We've worked on recognizing and solving stars bars problems, and now we're going to take it up one more step and combine it with some inclusion exclusion thinking as well. So we're going to first look at some stars bars problems with some restrictions on how many trees, if you want to call it that, are allowed in each yard. We look at how conditions involving the OR operator and the at least quantifier are dealt with in these kinds of problems. And then we're going to use complementary reasoning, or what I call complementary reasoning, to take some hard problems and make them a little easier by solving some easier ones instead and using those to solve the harder problems. All right, so here's an example of the type of problem that I'm talking about. So you have 25 trees and you're putting them in 8 yards. And suppose you want to put at least 4 trees in the first yard. Could be more, but at least 4. And at least 5 trees in the third yard. The question is, how many ways can you distribute the trees between the yards given those conditions? Well, this is a little different than the problems we were solving before, because before we had complete freedom to distribute the trees however we want, and now in the first and third yards we're given these extra conditions. So the strategy that we're going to employ is separate the problem into 2 parts. The first part is, let's first do the things we have no choice about. And once we've done the things we have no choice about, determine the things that we have complete freedom about, and then make sure that there isn't a third choice where we have partial freedom or something like that. Show that the ones where you have no choice and the ones where you have complete freedom are the only possibilities, and then use that to count the total. So in the problem above, the one thing we have no choice about is we have to put 4 trees in the first yard and we have to put 5 trees in the third yard. Now those may not be the only ones we put in there. Maybe later we can put some more, but we don't have to. We have complete freedom on whether we put more in those yards or whether we just leave them at 4 and 5. And speaking of complete freedom, the thing we have complete freedom of once we put those 9 trees in the first and third yards is we can put the other trees wherever we want. So after we place our 4 trees in yard 1 and our 5 trees in yard 3, that gives us 16 trees left to distribute. And again, these trees we have complete freedom to distribute them. We have 8 yards that we can distribute them to, and we have complete freedom about which yards that we put them in. So that means we have 7 fences. Since we have 16 trees and 7 fences, now we know how to count the number of possibilities, right? We add up the trees and fences, that's the 16 plus 7. And if we are fence people, we do that number choose 7, so we get 23 choose 7. Or if we're tree people, we do 23 choose 16. All right, so let's do one that's a little bit harder than this. So now you can either put 4 trees in the first yard or 5 trees in the third yard. So you have a choice, or actually you can choose, it's an inclusive or, so you can choose to put at least 4 trees in the first yard and 5 trees in the third yard. So you can do one, the other, or both. Now how many ways can we distribute the trees between the yards? All right, so what we're going to do is we're going to break this up into both possibilities, right? One possibility that makes this true is you can have at least 4 trees in 1 yard, in yard 1. So let's count all those ways because those are going to be part of our solution. So we have to put 4 trees in yard 1. And again, we could put more, but we have freedom about whether we decide to do that. That we have no choice about. That leaves us 21 trees that we can distribute wherever we want. And we can distribute them in any of the 8 yards, which means we're going to have 7 fences. So if we want to count up the total number of ways, we add our trees and fences. And then if we're fence people, we get 28 choose 7. If we are tree people, we have 28 choose 21. The other possibility is we could have at least 5 trees in yard 3. So to count those possibilities, we put 5 trees in yard 3. We have no choice about that. That leaves us 20 trees to distribute wherever we want. We again have 8 yards that we can distribute those trees to, so we have 7 fences. And if we want the total, we add our trees and fences. And if we are fence people, we get 27 choose 7. If we are tree people, we get 27 choose 20. So it makes sense. We found all the ways we can get at least 4 trees, all the ways we get at least 5 trees. It makes sense that we might add those two together. But you're too clever to fall for that trick. You can see that some of those are going to get counted twice, right? In fact, anything, and that means we're going to have to use the principle of inclusion and exclusion. So if you think about it, the ones that get counted twice are the ones that are counted in the first set of possibilities. You have to have 4 trees in yard 1. As well as the second possibilities, you also have to have at least 5 trees in yard 3. So now we get to count the number of ways that we can get both of those things, and then we're going to subtract that out at the end. So, well, and you know what? I think we might have done this problem, right? We placed the 9 trees in yards 1 and 3, 4 in yard 1 and 5 in yard 3. We have no choice. We have 16 trees left to distribute wherever we want. We have 8 yards, which means we have 7 fences. And so if we want to count the number of total number of ways, we add the trees and fences. And if we are fence people, we get 23 choose 7. If we are tree people, we get 23 choose 16. And now if we want to get the grand total, we take the number of ways that we can get at least 4 trees, add in the number of ways we can get at least 5 trees in the third yard, and then subtract out the ways we can do both of those things, and that gives us our correct count. All right, so I'm going to introduce you to another form of problem solving using these types of counting techniques. We're not going to work out an example. I'm going to let you think about that in the in-class activities, but I will give you a heads up about the type of thinking that you're going to do. So this thing, I call this complementary counting, and it happens when you have a big set and when you want to count part of the objects in the set. Now, we've actually already done this in the previous problems, right? Our big set was all the ways you can put your trees in those yards, and our part of that is the ways you can put the trees in the yards with those extra conditions on there. However, in those situations, we could actually count directly what it is that we wanted to find. Suppose that in this situation, we are trying to count something, but directly counting it is too hard for us to do. There is sometimes another way of doing this if we're being clever. So I want to sort of visualize this. So imagine there's the big set. So the big set contains, on the inside is all the possible ways we can count stuff, right? So one of the ways we can do this is we can count the objects in the big set, and then we can split the set into 2 subsets, one of which is the stuff we want to count. So that happy face over there on the left, that's the stuff we want to count. And the unhappy face on the right, those are the objects that we don't want to count. Now, we've already determined that counting directly the stuff in the happy face is too hard. So what we can do instead is, after we've counted the objects in the big set, we can take that total and subtract out the total of the objects that we don't want to count. In other words, we count the number of objects in the unhappy set, subtract that out from the big set, and when we do that, we get the total of the objects we do want to count. And if it just so happens counting the objects in the unhappy face is easier than counting them in the happy face region, then that will still get us the number that we want. All right, so I'm going to let you explore this strategy in the in-class activities, and that is in the PDF file called Stars, Bars, and Pi that is included with this video.